Dear all, I'm very happy to be here today to talk about REM sleep and neural circuitry. Although I will use paradoxical sleep rather than REM sleep globally, because you know that I'm talking from here, the Center of Neuroscience of Lyon, in fact, the neuro building named Michel Jouvet. So I've been continuing to work on paradoxical sleep, and I prefer to use paradoxical sleep for the last 40 years. And so my idea is to share with you the results we obtain with this network. So I want to go back, first of all, to the discovery of Michel Jouvet. And this is, of course, the Pontine cat, as you might already know. So if you remove the brain, you remove at that time the forebrain, so you have only the brainstem. And with such preparation, he was able to find out there were a period of muscle atonia, as you can see here, with rapid eye movements. So you see they were regularly occurring, this period of muscle atonia. So he went back to the intact cat and demonstrated that there was EEG activation at the same time, and that it was therefore corresponding to REM sleep described 6 years before in human by Aserinsky and Kleitman. So it means that the brainstem is necessary and sufficient to generate the state. And then he made many lesions, and he found out that if you make a lesion in a small nucleus named sublaterodorsal tegmental nucleus, SLD, in the dorsal brainstem, then you have no more REM sleep, or at least you have finally some RBD, REM sleep behavior disorder, phenotype a long time before its discovery by Mauralda and Schenk in '86. Since that, we did elaborate a lot and work a lot to detail the network, the neurotransmitter responsible for inducing the state. So here you see that there is an interplay between a wake system and REM, PS on system, and a very specific PS off neurons, which is slightly different than the wake system. So the wake system, hypocretin, histamine, serotonergic neurons of the dorsal raphe, locus noradrenergic neurons, they are both all active during wake, and they are inhibitory to the state of paradoxical sleep. But then you have a specific system, which is we discovered and located in the ventrolateral pyramidal gray here, which is GABAergic, and this system is inhibiting the SLD during wake, so that you don't have muscle atonia during wake. And for example, the hypocretin neurons, they are exciting this system, so that you are sure you don't have muscle atonia during wake. Then, so how do you go from there to paradoxical sleep? So we believe that, and we have evidence for that also, that MCH neurons and also GABAergic neurons, so it's a different population in the same area of the hypocretin neurons, they start to be active at the onset of the state, and they inhibit all wake system. And also they start to inhibit the VL-PAG GABAergic neurons, which are inhibiting the SLD. So by this means, then SLD neurons, they are disinhibited. So they can start to generate muscle atonia during the state of paradoxical sleep by means of a projection to glycine GABAergic neurons located in the ventral gigantocellular reticular nucleus. At the same time, you have also additional GABAergic neurons in the same area, which are taking care of inhibiting locus noradrenergic neurons and dorsal raphe serotonergic neurons. So there are a lot of studies, recent studies confirming this network. And of course, it's not a story over. I mean, it's not never over. Maybe there are other structures, but still we have a big idea here. So what we did also is that it's okay, we are not the only one. We did, but first inactivate these two players to see what happened. And compared to Jouvet, we did just inactivate one gene, which is a vesicular glutamate transporter 2. So if you inactivate this gene, specifically in SLD glutamatergic neurons. So it's a permanent inactivation in rats. So what's happening if you make this? You have a RBD phenotype. Just by inactive one gene in neurons, neurons are still alive, but they cannot release glutamate. You have muscle activity here during partial sleep. So it's a nice RBD model. If you do the same, but this time in the GIV glycine GABAergic neurons, the same, you inactivate only the transporter, GABA and glycine vesicular transporter, no GABA, no glycine transporter anymore. So if you look at the phenotype of the animal, you see they have also RBD. So they have the nice theta activity. They are inside partial sleep, but they have a very strong movement. So this was proving that this system really exists on the pathway and its neurochemical future. Now we are using a new transgenic mice model. And I believe, of course, this is the future, to use complex transgenic mice model to find out all the specific pathway. So we are using that. And basically, it's a bit too complex genetic model to be explained. But what you have to remember is that this model, if you have a stimulus, let's say you do a stimulus to an animal, then you inject 4-hydroxytamoxifen, 4-HT. Normally, at that time, if you induce a stimulus, you have C4 expression, but it doesn't last. After 2 hours, it's gone. But here, if you inject 4-HT, your reporter gene will continue to be visible even after 1 week or even more. So then if you do to the animal a second stimulus and you perfuse the animal, you can combine the TD tomato, the red staining and the C4 staining. So you can compare the activity. For example, here in this case, TD tomato is wakefulness, labeling neurons activity during wakefulness, and C4 is neurons activity during partial sleep rebound. So you can compare the two systems. Furthermore, because these neurons here, they also express CRE, you can use these trap mice to identify the function of these neurons using optogenetic, chemogenetic, cell-specific anterograde and retrograde track tracing, calcium imaging, single-cell RT-PCR, and so on and so on. So that's a very powerful method. Now, if I go to the first result we obtained, is that in this case, the idea was to make a whole brain mapping of the neurons' activity during wakefulness, first condition, and second condition during partial sleep rebound. So red, wake, green, partial sleep rebound. These are more control conditions where you have the two same conditions in the same animal. So in the same animal, you deprive the animal. Of course, you need also to deprive the animal. And that's a bit unfortunate to have a C4 expression during partial sleep. You need to deprive the animal of 48 hours with an automatic deprivation system, as you can see here. Then you stop this system and you look at the recovery. You increase up to 30% of partial sleep quantity after the deprivation. This is the homeostasis of the state. And if you perfuse the animal at that time, you see the neurons activated during partial sleep. So if you look at the same in the same animal to the two labeling, so you have wakefulness in red, you have REM sleep in green, and if neurons are activated during the two states, they are in yellow. So if you look at here, the brain, the cortex, you see it's not rarely the case. Most of the neurons activated during partial sleep are stay green. They are not red. On conversely, wake, red, there are only a few ones which are activated during partial sleep. It means that the two states have nothing in common now. That's a very important new message, contrary to what was thought for decades. Also, paradoxical sleep is not an activated state during like wakefulness. It's more deactivated, excepting a few limbic cortices like the retrospinal cortex and dentate. So this is a very peculiar state, very different from wakefulness. if you look at, again, the distribution of neurons in the cortex, you will see that there are more activation during wakefulness here. This is clear than during paradoxical sleep, even in these few structure activity during the state. So really, paradoxical sleep is not very active, but there is activity in the retrospinal cortex, claustrum, medial cortex, different neurons in wake. Okay, you could say, oh, that's just CFOS, but we did record the neurons there in the retrospinal cortex, for example, and we found out that there a large number, majority of the neurons, they are more active during REM than during active wake, even, or slow wave sleep, like 57% of the neurons. Activity correlated with theta also. So that's a very nice region important for the state of paradoxical sleep. Now, if we go to the hippocampus, it's also very interesting because in the hippocampus, you have more activity in the dentate, here in green, than during wakefulness. You can see the green neurons are more numerous than the red neurons. So clearly here, the dentate, which is a key structure for learning and memory, is more activated during paradoxical sleep rebound than during wake. And this structure is key for learning and memory. So it means you have something to do with learning and memory. You activate memories during paradoxical sleep more than during wake. So if I summarize the story here about the cortex, at least, so we have a few limbic cortices activated during paradoxical sleep, like the medial cortex, the retrospinal cortex, the intercingulate cortex. These structures are activated by two subcortical structures. We found out the claustrum and the supramammillary nucleus. And this is very specific to paradoxical sleep. What is the function of such very specific activation? Of course, we believe it has something to do with the function of the state. And also, I mean, it would make sense. It has something to do with dreaming. And in fact, retrospinal cortex is known to store scenario. So, I mean, it's likely that it replays a scenario during paradoxical sleep. Even when there is a motor component, then you activate the motor cortex, and then you don't activate the spinal motor neuron, although you put glutamate there, but you have the inhibitory system, so you are safe. You can, for example, test new behavioral motor strategies during the state because you have muscle atonia. So I would say that it's much more complex than just a replay of memory. That's the idea, and we are working on the real function of such activation. And this is the team which is doing the job in the lab, and I'm very happy that they are there. They are really extremely well doing the job, and I hope I will answer to the question of the function of paradoxical sleep soon. Thanks a lot for your for listening to me. I'm glad I was there. Thanks a lot. Bye-bye.